Dear world, welcome back to the next session of strings, ternary search trees. Previously, we have studied the prefix tree, then we have studied the compressed prefix tree, and now we are right now in the ternary search tree. So today we will be understanding the ternary search tree. Not only we will be understanding the ternary search tree, we will understand the concept. Then we will understand the code, how the concept is getting converted into the code. Then we will practice the code. We will write the entire code after understanding the entire concept. So the aspects that we will discuss in this video. First, concept of ternary search trees. First, we will be learning the concept of ternary search tree. Second, why TSTs. That means why do you require ternary search trees? We will know that reason because there is already previously prefix trie. Then we got compressed prefix trie that optimize the memory space. Although we have those trie, why do you need the TSTs, that is ternary search trees? We will discuss that one also. Then key characteristics. What are the most important characteristics of ternary search tree? We will be discussing that things. Next, all ternary search trees operations, insert, search, delete, all operations we will be discussing one by one, and at the end we will be discussing the time and space complexity. So the picture that you can see in the right side, this is actually ternary search tree. This picture that you are currently able to saw, that is ternary search tree. This is the photo of ternary search tree. So before I tell you the ternary search tree, let's have a look of the code that we are gonna actually write after the program, because we are programmers, so we should have a friendship with codes always. So let's have a look of just the code. I will not make you understand, just a look. So okay, this is ternary search tree, and this is the string algorithms. We have already completed a lots of algorithm, and later if there are some algorithm that we have not discussed, we will be discussing in the next later videos. So you can see ternary search tree. Look the implementation. First, what we have done, we have created the TST node. That means we have defined the nodes required for creating ternary search tree. Then we have started implementing the class ternary search tree. That means from here we start writing the main body of ternary search tree. After that, from here it start our insert method, and look, inside this insert method we have used a recursion, root insert recursive. That means we have applied here recursion function. Look, this is the point to remember. We have applied recursion function. Not only here, in all the aspects of this program we have used this recursion very importantly. So this is insert recursive. Now let's again look the search. There is also the recursion, search recursive, and there is display, there is also the recursion. So as you can see that we have applied the recursion here most importantly. Next, from here we have called the main function using the TST demo, and we have got the output as expected. So that is the program that we all gonna write after understanding the concept, after understanding that how we can write the codes one by one, after fetching the concept from after understanding the code. Okay, so move back. First we will understand the concept that what is ternary search tree. So the name what suggests is that it is a hybrid between binary search tree and a trie. Look the name ternary search tree. Why the name is ternary search tree? Because it's a hybrid. Because it's a hybrid between binary search tree and trie. Binary search tree plus trie. So this is, we can call the trie as the combination of binary search tree and the trie. So as you know that binary search tree, what happens in binary search tree, that we have a node. Let's say we have a node, and then from there we have again two nodes, from there we have again two nodes. So this is the implementation of binary search tree. And what happens in trie, that we have a root node. In trie we have this is binary search tree implementation, BST. Now we are looking at trie. So what happens in trie, what we have observed in previous video, that there would be a root node, then there will be a character. Let's say this is A, and now this can have a lots of pointers in tries, in regular tries. So the combination of binary search tree and trie, this entire combination form the ternary search tree TSTs. So that form the combination ternary search trees. As you can observe, this combination forms the ternary search tree TSTs. And as you can see the picture, this is the combination of both the binary search tree and the trie. So now we have understand the concept of ternary search tree. Now we will be understanding the concept that why do you need ternary search trees? Why do we actually need ternary search trees? Then I'll tell you that how we can insert a word, like there is word apple, there is app, and there is bee. How we can insert those words inside this ternary search tree? So why TSTs? The important aspects of TSTs. First aspect, that is efficient search. Efficient search. That it performs operation like search, insert, delete in more memory efficient manner. Any operations, that is first what we perform is insert operation. First to insert, then search, then delete, etc. operations when performed on ternary search tree are performed in memory efficient manner. That means here the memory is reduced, here only a small portion of memory is used, so memory efficient. All operations here is memory efficient. The second is the important things here is that is different from the binary search tree is middle character ranking. Second is middle character linking. What we do in ternary search tree, that we always link the middle character linking. So this is one thing that is different from the binary search tree. As we have seen in ternary search tree, the structure of trie. The structure of trie is, let's say this is our root node and there is another root, and from there are lots of things are there. In binary search tree the structure is quite different, there is only two nodes. But in ternary search tree the structure is very different. This is hybrid of those, that is there is middle character linking. So the structure of ternary search tree is like this. First we draw a binary search tree. So this is a binary search tree and middle character linking. Now we will be linking using the middle character. So we use a middle character linking and this becomes the ternary search tree. Ternary search tree. So this is the actual structure of ternary search tree that you have observed in the beginning. And the third important aspect of this, that it is like a balanced tree. It has a balanced tree like structure. Balanced tree like structure. You might be thinking that why balanced tree like structure? Because it allows you to have the performance of a trie and the memory usage of a binary search tree. Because tries are very much performing, so it utilizes the performance of a trie. It utilizes the performance of a trie. Because trie are very fast. It only takes a time of big of m, that means a time equal to the pattern length. So performance of a trie, this is trie. And memory efficiency of a binary tree. Memory efficiency of a binary search tree, BST. Memory efficiency of a binary search tree, that is BST. So that is why so these are the few important aspects of ternary search trees. So we have understood the why do you need ternary search tree. We have also got to know that what are the key characteristics of ternary search tree. Now we will be understanding the insert, search and delete operations. So before we understand the insert, search and delete operations, we will be understanding the concept that how we can insert elements. So as you can see that apple, the word apple, here first we have inserted a p p p l e. So let's understand, let's analyze this example that how everything is happening here. So we are coming to the next page, apple. The word there was apple. First word was apple. First, whenever we start anything of try, we declare a root node. First, what do we do? We declare a root node. So observe, first we will be declaring a root node. So let's say this is our root node. This is our root node and we declared a root node here. That is the root node we declared here. This is the root node. So after declaring root node, we try to insert the A. First, while now we are in this apple letter, A double P P L E, and our current pointer is in the A. So first we try to insert the letter A. So this is the root node and now we try to insert here A. We inserted the letter A here. So as you can see that this is a node and it has the letter A. Now observe, we have inserted the letter A. Now we start searching for the common structure of ternary search tree. What we observed in ternary search tree that it has three pointers. It has three pointers, the left child, the middle child and the right child. Left, right, middle. It has three pointers. Three pointers. It has three pointers. First, left child. Left child. Second, right child. Right child. So do you know what the work of left child is? Left child always stores those characters which are lexicographically less than this letter A. Which are lexicographically less than this letter A. That means it stores or points lesser character than current node character, that means it stores, suppose there is not A, there is C. So the left child will store those letters which are lexicographically less. Lexicographically, that means dictionary wise. You might be thinking what is dictionary wise. So let me tell you lexicographically. Lexicographically. So lexicographically, the meaning of lexicographically is dictionary wise. That means if there is word, app, apps, there is bat, there is cat, cow. So the order will be them first app, bat, then cat, then cow. That means it follows the dictionary order of A. That means, so if there is some letter like CAT, suppose there is CAT. So when there is C, the left, this is A. A is lexicographically lesser. That means it comes before C. So it will come at the left child side. This is here. The T, it comes after C. It comes after C. So it will move in this side. This just actually follows the simple English ABCD type of ranking. Simple A, B, C, D, E, F. So if this is our root node, if our root node is pointing this place, so all those characters will come to the left side, it will come to the left side, and all those characters of that side will come to the right side. That side will come to the right side. So this is lexicographical meaning. So I made you understand. So let's come back to the insertion. Okay, come back to the insertion. Left child and right child. It stores greater than elements, greater than characters. So this is the left and right child. And the mid child, there is another child that is mid child in ternary search tree. It stores the characters. Look, there is some speciality. These two stores character of another word. Those two stores character of another word. But the mid child always stores the character of same word. That means here all the characters of this word apple, it will get stored only in the mid child. That will get stored only in the mid child. So those all characters will get stored in the mid child. But of other words, character, app, bat, those characters will get stored in the left or right child, left and right child and right child. So this was the concept. So the mid character stores mid character stores characters of same word, characters of same word. So now after A is inserted, we come to the P. We come to the P. Now after A, we insert P in the middle. Look, we insert P in the middle. There is left and there is right. After P, we again come to this P. Now we again insert P. After P, we come to L. Now we insert L. After L, we come to E. Now we insert E. So we have inserted successfully the word apple. When the insertion is done, we use the boolean flag. What we use? We use the boolean flag is end of string as false or true. So here we will change the is end of string. Now the boolean flag is end of string will change this value to true. Why? Because this is the end of, because that is the end of a word. If that is the end of a word, we mark this boolean flag as true. So we have marked it as true. Now we come to the word app. Apple has been inserted. Now we come to this word app. So let's, okay, now we'll try to store this word app. So now guess, suppose our pointer is right now on A. Our pointer is right now A. So we'll try to insert A. Now we'll check from the root node. We'll check from this root node if there is A somewhere left, right or mid. But in the mid we have already got A. We have already got A. So no more further we'll check. We'll just come to here. That means now we are not inserting A. We are just ignoring A. Now our pointer comes to P. Now we again check that if there is P or not. Yes, there is P. So we will not check anymore. So now we come to the letter P. We come to the letter P, and in P we will again check from here. After inserting A, we will check from here if there is P in any wise. There is left, right or mid. Yes, there is P. So we come to this here. We again ignore inserting P. We again ignore inserting P. So after AP, we again check if there is E. We again check if there is E. Now observe, from P when we check E from left, right, if there is E or not. But now we don't get this E. Now we don't get this E. So what we do, we now create a new node. We now create a new node. But in which side we need to create that new node, that is important. Now we check what is there from this P. There is already a P in the mid position. And what is E? So E is, what is the value of E? That is greater than, that means it comes, the if the E comes before P or after P. So if you take like A, B, C, D, E, F, dot 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 P. So P always comes before E. So the P will be inserted in that side. A, P. So now in that side we will be inserting the P. So now the P gets inserted in the left side. APE, because it comes before, the E comes before the P. So we insert in the left side. If it would come after the P, we would insert in the right side. So now this is done. We also inserted this word. Now we are coming to word bat. So while inserting this word bat, when our pointer is in the B, we check from here. We again check from this same position. If there is B somewhere. Now look, there is not B, but there is A. Now we again check the lexicographical order, that if B comes before A or after A. Now look, there is A and B comes after A. So insert the B in the right side. Why right side? Because it comes after A. B comes after A. So insert in the right side. So inserted here the letter B. So we have inserted. Let me clear those places. Okay. After B, now we check from here if there is something in those 3 pointers. But those 3 pointers are null. They are not pointing to someone. So now we need to insert the second A letter. So we create a letter A in the mid position. Got it? We create in the mid position. We always use this mid position for inserting the characters of same word. Now we come to T. We again check if there is T in any side. No. So insert it in the mid position. So that is the bat insertion. This is how we insert a full node. So now let's move to the beginning to check in more details. What we have done here first, this is loop. There is a root as I mentioned you, and now I'm telling you the architecture, more diagrammatic architecture. This is the root, and do you know the root is actually root? There is nothing, there is no value. So the root is having actually empty value. It is having actually empty value. The root is having actually empty value. Now it comes to a, when we are in the apple, when we are actually in the apple, so we first insert a. So first we have inserted this a, so a got inserted. So if you analyze what this a is having, if you analyze this a, so let's this is the pointer. First it is having a character a, then it is having a boolean flag, is end of word, is end of word. This boolean flag is end of word, it marks true or false, either true or false. If that is true, that means that is the end of the word. If false, then that is not the end of the word, that means the word is continuing. So in this case, by default it will be false. And now there is three nodes. There is three nodes. This is containing three nodes. Pointer for left, left, mid, and right. Now as you can see, from A we come to the mid position. Now A is linking to this mid. From A we come to the mid position, because we know that whenever we insert the second character of the same word, we always take mid. So in case for the second letter P, we again took the mid. For again the P, we will again take the mid. We again took the mid. Again we will take the mid for L. For L we took the mid, and after E, for E also we will take the mid, because for same word, for the characters of same word, we always take the mid pointer. What we take? The mid pointer. So we took the mid pointer. All the mid pointers are taken. All the mid pointers are taken for the same word. For the same word, same word, same words, same words character, same words character, and the word is here apple. The word is apple. So we understood in ternary search tree we always use the mid pointer for the insertion of all the characters in one same word, in one same word. Now come, apple has been inserted. Now we will try to insert the app, APE. So first we again look from root if there is a existing, that means a, if a is already present. Yes, a is already present, so we came to a. From a we came to P. P is also present. From P there is no. We check if E was present, and E was not present, so we created the E in the left side. Why left? Because it is lesser than P, so left side E. And now APE, so the word is finished. We marked here E as the true. We marked the boolean is end of word flag as true. We marked here as true. This is end of word. Now again we came to insertion of bat. So there is not existing B. So we created the B here. Look, observe B. Oh, actually here this is another example. Here APT apt has been inserted, but if we would insert bat, then we would insert from here B. From here we would insert the letter B, then we would insert the letter A, then we would insert the letter T. So the diagram is of actually not of bat, it is of APE and APT. APT. That is the diagram. So that is the introductory diagram. We got understood the ternary search trees. Now let's move to the next concepts. As I told you the ternary search tree, let's study from here what it tells. A ternary search tree is a hybrid between binary search tree, hybrid between a binary search tree and a trie. As I told you that it's a hybrid architecture between binary search tree and trie. Key features: each node, like a binary search tree, it stores data in sorted manner. Look, it also stores data in sorted manner. Important things that it stores data in sorted manner. That means what we can say, that TSTs store data in sorted manner. It stores data in sorted manner. Like a trie, it is highly efficient in handling string and provides fast looking nodes. Now, as I told you, the TST is having three children nodes: the left child, the middle child, the right child. Left child stores character less than the current character. As I told you that whatever the current character, if that is less, it will go to the left side, and if it is greater, it will go to the right side. So character is greater than the current right character. And middle child stores the next character in the string. In the string, if the string has a same, look, it stores the next character of what, of the same word or same string. So we missed a word of the same word, or same string, same word or same string, same word or same string or word that is same. Character wise search is to store character of a string in a way that tree can facilitate searching for any word. Okay. Now space. Three pointers, as I told you, that three pointer left, middle, right. This is, and look, the important thing is that boolean. There is always a flag boolean is end of string or is end of word. We can name it anything, but we mainly use is end of word. I sometimes use in the program is end of word. Sometimes I use the is end of string, whatever I want. So you can use anything as boolean flag, but it's better to use is end of word or string for memory purpose. We can remember it better. Now usage. Unlike a traditional trie where every node has multiple pointers, TST has fewer pointers, making it memory efficient. That means this is a good thing that TST is having only three pointers. And that's why it is more memory efficient. If you just observe a trie, it would have a lot. In general, TST normal trie can have 26 pointers, or it can have at highest 256 pointers also, as per the maximum ASCII range. Applications. Why we use TST? For autocomplete features in search boxes like Google, we use this TST. For dictionary applications, if you get some problems like dictionary applications and lead code or the longest substring, then you can use. For spell checking purposes, also you use this Ternary Search Tree. This is not VSCode, this is actually. So let's keep the theory concepts open so that we can understand it better. Okay. While we actually work, we'll be solving this example. So we are on the VSCode, and I have already defined the ternary search demo. But now we'll be deleting I'll be deleting the entire file of ternary search trees. Delete. Now look, right now my main directory, observe the directory. I'm inside the directory Java string algorithms, and where I will be working inside the directory tries, not tries, TSTs, because I'm working on ternary search tree. So first I need to change the directory, so I'll be using change directory command TSTs. Now code. Now I will be using different file for different things. For the declaration of node, I will be using the tst node.java file. So for that, code tst node.java. Okay, so the node has been now defined. Now let's declare the file public class tst node, public class tst node. And now first we have to declare the variables character data. This character data is for storing the character of the node, This is for storing the character of the node. This is character data. Now we need to insert the boolean is end of word to mark the end of the word. boolean is end of what. Now the 3 pointers TST node left, mid, right, public. Now we'll be declaring the constructor. The constructor is declared because we want to make the objects of this class completely reusable. Character data, this dot data equals to data, this dot is end of what equals to false, this dot left equals to this dot mid equals to this dot right, that is equals to null. Okay, so first time we have initialize the node initialization is done. The character data boolean is end of what, and the 3 pointers tst node left, mid, right we have defined. Then we have declared the constructor, the constructor public tst node, that actually declares the entire initialize the reusable object. So there, that is the declaration of tst node. So after creating the tst node, we'll be creating the file ternary search tree. So for that, let's write code ternary search tree.java. So for that, we will again use the public class ternary search tree. And now first we will declare the root. Look, as we saw in the example, we always saw what we did, that while before inserting anything we used to declare a root. And this root was completely null. So first in the program we also have to declare this root. In the program we have to declare this root at the creation of ternary search tree file. What we have created before, we have just created this node object. The node object, the character that if after root if you insert suppose c, so this is node. We have declared till now this node c, and what is actually contains this c node? It contains all those 5 factors. First character c is end of what, it contains is end of what, that we wrote in the code, and it contains 3 pointers left, right, mid. So we have declared the structure of this as this. So after this, now we'll be declaring this root at the initialization of our file. TST node, the node for ternary search tree root. Now we will be inserting a word into the ternary search tree. Inserting a word into the ternary search tree. Public void insert string word. We will be trying to insert a word, and root equals to, now from here will be called a recursive function. Why recursive? I'll tell you. Insert recursive root comma word. Will pass the word as character array, because we need character arrays to pass one by one all the characters, and we'll be passing 0 as the current index position. Now we'll be declaring this recursive function. Private, the return type will be a node, tst node, insert recursive, and now tst node, this is actually current node, character word, as the word's character will come as array format, integer index, current index. Now first we will be checking if the node is null. If suppose the node is null, that means there is already no character, so we have to create a character. So first we will be creating a character. If node equals to null, if node equals to null, then we will be creating a node. then node equals to new ternary search tree node. We will be creating a node with respect to ternary search tree node with respect to the first character of index. First character of word. So word of index denote the first character because it contains the value of 0. Later it will be updated. So word of index, this is if node equals create. So we created a node, created a node if the character was not present. So this was the creation of node. Now we'll be checking if the character is greater than or less than. So if word of index, that means the current word's character is either less than or greater than the data. If this is less than the data, then we need to insert in the left side. So node.left equals to insert recursive. We'll be again calling the recursive function, and that will be inserted in the that current node's left portion. Since insert recursive node dot left comma word comma index. So this is for traversing left, this is for traversing the left pointer for smaller characters than the current characters. Now the second condition, we will be checking if that is greater than the current node's data. So else if out of index greater than node dot data, else if greater than node dot data, then that will be node dot write equals to insert recursive node dot write comma word comma index. So now this is for write pointers for characters greater than the current character. After this, if both conditions are not satisfied, that means the character is present. So in that case, we'll be checking if that is the last character. That means if index plus 1 less than word dot length. So if that is word dot length, so we can insert the character. That means node dot middle equals to insert recursive node dot middle comma word index plus 1. So we are traversing the middle for the next character. Here we are traversing middle for the next character. Look, the insertion is always done for inserting a character in the mid position. Whenever we insert a character, we only insert the character in the mid position. And in other cases, if we don't insert, then we just traverse in the left side or in the right side. And we declare that left or right traversal using assigning on the node dot left part the left side node dot left, in that way. So after if else, either we insert or we return node dot is end of word as true. Here we mark the end of the word, Now we'll be returning the node, and after this else part we return the return node. So this is how we actually search the entire ternary search tree. Now we'll be implementing, after the insertion operation, we'll be implementing the search operation. Searching a word in ternary search tree. Searching a word in ternary search tree. And for that also we will be using the recursive function public boolean search string word return search recursive, and we'll again pass the root, then we'll be pass the word as character array, word dot to character array, and 0 as index, and from there we'll be declaring as private boolean search search recursive. We'll be receiving the root as the node. This node is here the current node, character of word and integer index. Now again we'll be checking if node equals to null. If node equals to null, that means there's nothing, so we should return false instead of approaching false. If node is not null, then we will approach if odd of index is less than the current node's data. Then we should search in the left side, return search recursive node dot left comma word index. This is for searching and traversing the left, searching in left. Now we'll check the second condition, else if word of index is greater than node dot data. If this is greater than data, then we'll be returning search recursive node dot right comma word comma index. Now after this if else if both conditions are not satisfied, so we will be checking if the index is equal to the length of the word. If index is equals to word dot length minus 1, return node dot is end of word. So if the is end of word is true, it will return as true, and if this is false, so this is false. This is for checking the checking if that's the end of the word, that's the end of the word. Otherwise we return search recursive node dot middle word. We increase the word count, so here the word is increased. So using this we can search the words. After the search operation, suppose we want to preview all those, we want to display all words in ternary search tree. For that we use the display function, displaying all words in TST public void display character buffer new character 50. We have created a buffer array to hold actually the characters of current word, to hold the characters of current word. We have created a buffer array of characters. Now from here we'll again use a recursive function, display recursive root comma buffer comma 0. Look, I'm getting in the suggestion, you might not, because I've practiced before also in this same code box. Private void display recursive, and now we receive the TST node character buffer and integer. We can call it index or depth. I'm using just depth. So first we'll be checking if node not equals to null. If node not equals to null, then we will be traversing in the left side, display recursive node dot left comma buffer comma depth. We pass the depth, buffer of depth equals to node dot data, storing the current character, Now we'll be checking if that is end of string. If node dot is end of word, then we'll be printing the word that's the end. System dot out dot println new string buffer comma 0 comma depth plus 1 display recursive node dot middle comma buffer comma depth plus 1. Now we are increasing our character count by 1. Now display recursive node dot right comma buffer comma depth. Now this is for traversing towards the right. Now that is the end of the class. So we can declare here a main method public static void main string args. Now we will be creating an object of this ternary search tree TST equals to new ternary search tree, and now we'll be inserting words into TST, inserting words into ternary search tree. tst.insert mango, tst.insert apple, tst.insert rose, tst.insert man, tst.insert wiki. So we are inserting all the words tst.insert hard prefix try. Okay, so we inserted all those words. Now we'll be searching words in ternary search tree. So searching words in TST, that is ternary search tree. System.out.println searching apple, tst.search. So now it will return us either true or false. We can do for another word also. We studied it do not exist, rosy. Okay, so it do not exist. Now we'll be displaying all words, and for that we'll be using the function tst.display system.out.println displaying wall words, and now we'll be using tst.display. This is for to display the words. Now let's compile the file. Java compile -d dot ternary search tree.java. So here is some problem. We got errors in that node.middle. Let's see this mirror in 56. Line number 56, there is some error. That node.middle is not defined here. Why node.middle is not defined here? There is mid. I think I should change this mid. Okay, let's change the middle here. Control F, because in node we have used mid. So now it will change the mid of all words. Now let's again try compiling. Now the file has been compiled and a class has been generated. Now we'll be running the file Java ternary search tree, and you can see that first we have got true apple searching, and second for searching the word we have written here apple, we should have written here rosy. So again we are compiling so that you do not get confused. Now see, we have got true for apple, but for rosy that doesn't exist, we got false. Now it displayed all of our words using the display function. We have created all words that we inserted. It has printed all those words starting from apple. So this is the insertion of ternary search tree. Now let's understand how this code works. inside few important aspects that why do you need that recursion. Now, so for that, again come back to our lecture part. This is ternary search tree. Now look, what happens that whenever we insert any word, look, this was the declaration of a node. I made you understand that that was a TST node declaration. This was TST node. And every time whatever we do, either we create our root node, we create this. If we create any pointer, we also create the pointer with respect to this class. This is like TST node left, so this is left pointer. Meet, this is meet pointer. Right, this is the right pointer. And do you know what this pointer does? They point to the next character. This. They point to this character that we have done in TST node class. Now we have used the recursion because look, if you insert this word from rat, this is the node, root node. Let's call it root. And now let's insert this word rat. So if you insert rat r, after we insert a, after we insert t, so we inserted this word rat. Now observe, when we'll again insert this word rat, rate. So now observe, we'll again come here and we'll check if rate exists. We will check that if r exists, that means here we take a decision. And in decision, you know, there are three major decision factors that either I have to move in the left or in the middle or in the right. In which side I have to move. This is first time. Notice here, this is first time we took the decision here, first decision. First decision, that is our first decision. Now again after inserting, now we just ignore the word, we came to the here because this is already available. So after from r here we check if a exists. Yes, a exists. Now a exists. So now we check in which side we have to move. As we got a, we will moving towards this. Here there are also three sides that where to move. As a was available, so we came to here. Now from here a, we again check if t exists. Yes, t exists. From here after taking decision, we again came to the mid. Yes, t exists. Now after existing t, now we check if there is any left, right, mid, what we have to insert. So this is not available. That means there is not any node. We get that condition. So we actually create a node here and we insert this e. And in both case, the boolean here is for true. Here is true, so that is the end of one word. Here is also true, boolean is, that is also the end of one word. So that is boolean is end of word. Now look, we take a decision second time here, we take a decision third time here. Now come this bat. We got completely new letter B and we check if B exists or not. Now we compare this letter B with this R. If B is greater than or less than or B is equals to R, what is? We take the decision that what is exist. And now we get that B is actually less than R, lexicographically less than R. That means in English alphabet B comes before R. So B will come in the left side. We will insert B here. So now that we took decision for three times. There are three major decision cases, and not only three. We take this decision every node. From here B again we come here and we insert A, then we insert T. So for same what they came, but when we again come to battle, after T we insert T. So we take that type of decision again and again repetition. In every node we have repetition. We have repetitions of repetition of decision, and because of this repetition we use the recursion. We use the recursion. Cause of this decision we use the recursion plus DP, dynamic programming, and that is why we have used so much recursions. I have already, this is the code, class TST node. Look, class TST node, character data, boolean is end of what, which marks if that is end of what, left, right, mid. These are the pointers, left, right, mid. So these are the pointers, and here we have initialized. This is called constructor, public TST node, that is called constructor. And constructor creates exact instant reusable object. That means if we create an object of this node, we can use it instantly. Because why? We have defined using constructor. So that is constructor. Okay, so this was after declaring the node, we have started using the public ternary search tree. And now look, in the public ternary search tree, we have defined our root node here, TST ternary search tree node root. This root node we have defined, that is the root node that I am telling you again and again. Now I have inserted from here public void insert, and in this insert function I have used recursion. Insert recursion. From here we have passed root. We have passed this root address reference. Then word dot to character array. That means the entire word apple gets convert. Apple get converts into apple. A P P L E. They gets convert into characters. They gets convert into characters, and this is where moving. And this is the index 0. Now they are being accepted here, here, and here in the node section. Now we check the first condition, that if there is not node, if node equals to null, that means if the node is not pointing to null, then we create here a new node. We create a new node. And how we are creating? Using the new tst node function. New tst node word of index. Using this we are creating a new node. We are creating a new node. Okay, after we have created a new node, if there is not null, that means this was the empty case. For empty case we have created a new node, but for the cases where greater less than, we have checked through this. That means if a equals to a less than b, a greater than b, or a equals to b, we check this condition. This condition is if word of index, that means current word a, less than b node dot data. If that is less, then we apply this, that means node dot left. We channelize, if suppose this is a, then we channelize our program to move towards this side. We channelize to move towards this side, because this is node dot left does. This is used for channelizing. Second case we have checked if greater. If that is greater, then we channelize in the right side. We channelize in the right side. And if that is not the case, then we check if our correct index plus 1, that means next index also is less than word dot length, that means there is more character, so we actually insert one more letter, insert plus 1, and we come to the mid. That means from here we insert next character. So this is how our insert recursive is working, and at the end we return the node. That means the address of this node gets returned here, so it points to actually this, and the entire tree is being constructed. Okay, so after this is search recursion, same as we observe. After search recursion, that is display recursion, same. We have created this is buffer array that we have created, and after buffer array we are again sending display recursive. We are sending the root, we are sending the buffer array, and then we are sending the current index. We are checking if node is not null. If the node is null, that means there is nothing, we would just return. So if node is not null, then we are first running display recursive, because here we are using that is called pre-order. That means left, mid, right, and this is I think called in order. We are using here in order traversal. So we have used left, middle, and right. So this traversal we have used. We are checking this node dot left buffer depth. Buffer of depth equals to, we are storing the current character into buffer of depth, and if node dot is end of word, if they are telling that is the end of the word, then we are printing that current buffer. That means, because whenever this is end of word always tells us if that is the end of word. If that is true, that means that is the end of the word, and if that is false, by default always this is false, that means that is not the end of the word exists more. So that is the entire function we have discussed. Big of login, those all takes big of login in average case. Average case that takes the time of big of login, where n is actually the number of nodes. This n actually denotes the number of nodes. This actually denotes the number of nodes. And if in case of worst case, if the tree is not balanced, in case of unbalanced, the time complexity goes up to big of n. It hikes up to big of n. Whereas the space complexity for ternary search tree is always n. The space complexity is always big of n. Where n is the total number of characters in all the string stored in the ternary search tree. Where n is the total number of characters, stored in the TST, stored in the ternary search trees. So we got the time complexity also. Now we are ending this video here. We have discussed all the important factors, the time and space complexity also, that there is two type of. Mainly in average case, the time complexity is big of log n, and in case of worst case, if it moves to worst case, then it comes up to big O of n. It comes to big of n. So this is the time complexity. Whereas the space complexity, this space complexity is always big of n. The space complexity is always big of n, where n is the total number of characters. Total number of characters. So that is all about ternary search tree. We'll be meeting in the next video in the suffix tree part. Until now, keep enjoying, and we'll be discussing all the lead code to solve problems also regarding that. But first, let me cover you the theories. So for now in this video, we have actually till now have covered what? Prefix trie. We have covered the prefix trie, then we have observed the compressed prefix trie, and after compressed prefix trie, we observed the ternary search tree today. So in next video, we will be actually observing the suffix tree, because this is also important of suffix tree, which is a part of strings data structure.